here we have completed the first two chapters. That is, first one is electrostatics and the second one is electric current. In the electrostatics, we are going to see about the static electric charges. So here our hero is the charge, he is not going to move at all. Here he will be static. Then in that, what are the forces acting on the charges? Because of the forces acting, electric field we are gaining. What is the electric field? How to measure it? And what we are seeing, how will be the force of attraction between any two charges? And what is the capacitance? This and all we have seen in the first chapter, electrostatics. Here the charge is your hero, he is not going to move, he is static. Then now what happens if the charges move? We are gaining current. That we are going to see in the second chapter. Whenever there is a current, there will be something to resist the flow of current. That we call it as a resistance. So what happens to the resistance when they are connected in series, in parallel? That and all we have seen in the second chapter, electric current, isn't it? Then applications, that and all we have completed in the second chapter, electric current. Now whenever a current flows in a conductor, what is the effect you are getting? What happens when a current flows in a conductor? So just imagine this is a conductor. Here in a conductor there will be so many free electrons moving in a random direction, isn't it? So if I apply a external potential to it, just connected to external battery, I am supplying some voltage to this conductor. What happens when I connect it to the external battery? All the free electrons, already we have seen this in the second chapter, when all these free electrons which are moving randomly will get accelerated because of the external electric field, and they will move in a definite direction. That constitutes the electric current. So the electrons are accelerated by the voltage V. Let V be the voltage you are supplying to this conductor. Because of this supplied voltage, these electrons are accelerated. That gains them energy. When they gain some energy, what they will do? They will move in a definite direction. When they move like this, they will collide with each other, that is with the ions of the lattice atoms or with each other. When they collide like this, a part of its energy is wasted in the form of heat to the conductor. Yeah, that we call it as the heating effect of electric current. So how we are getting that heating effect? Due to the collisions of the electrons when they are accelerated by a external battery. So these accelerated electrons, when they move from one end to another end, they will collide with the lattice ions or atoms. When during this collision, a part of its energy is given to the lattice ions. So this happens in due course. What happens? All the lattice ions will gain some energy. This we call it, this energy what it gained, we call it as the thermal energy. Thermal is nothing but the heat energy. So this heat effect is nothing but the effect due to the flow of electric current. Whenever the current flows, what happens? A part of its energy is given up in doing some useful work. For example, there is an electric motor running or a bulb is glowing. Clear? Let it glow for some time. How the bulb glows? Because of the flow of current. Clear? The flow of charges. When the bulb glows for 10 minutes or 20 minutes, then you go and touch it and see what is the effect you can feel. You can feel some heat, isn't it? How we are gaining that heat or thermal energy? It is due to the collision of the electrons with the lattice ions or atom, we are getting that heat energy. So whenever some work is done in moving the electrons by supplying a potential V, that work done we can take it as work done equal to V into Q. Then what is Q here? IT. Let I be the current flowing in the conductor for a time t. So this work done will be stored in the conductor in the form of thermal energy. This thermal energy we call it as the heat energy produced in the resistor. So whenever a current flows in a conductor, a part of the energy is used in doing some useful work and the remaining part of the energy is dissipated in the form of heat. Yeah. So this we are going to see in the third chapter, that we call it as the heating effect of electric current. So whenever a current flows, there is a heating effect. The current produces thermal energy, isn't it? So if I use this thermal energy to produce a EMF, that reverse effect we call it as the thermoelectric effect. So using thermal energy, if we produce an EMF, that we call it as the thermoelectric effect. Yeah. So in the third chapter, we are going to see about the effects of this electric current. So far in the first chapter, we have seen only about the charges at rest. Then we are in the second chapter, our hero, that is a charge, is going to move. When he moves, we get the electric current, and what are the things in the electric current, what is the resistance, that and all we have seen in the second chapter. And here, because of the charges moving, what are the effects, that we are going to see in the third chapter. The first thing we have seen, what is the main by heating effect of electric current. Whenever current flows, a part of the energy is useful, is used in doing some useful work. Whenever a motor runs, the motor is running, it is pumping the water, that is useful work done by the current. But when it runs for some time, I can feel the heat energy. So a part of its energy, we are not going to use the full effect of the current in doing the useful work. The full effect, the full part of its energy is not used in doing the useful work. Some part of its energy is wasted, is dissipated in the form of heat in the resistor. That effect we call it as the heating effect of electric current. We know that already. Whenever a steady current flows in a conductor, there will be a magnetic field around it. Because of that, it gains the magnetic effect also. That we call it as the magnetic effect of electric current. That also we are going to see in this. So both we are going to see. One, the heating effect of electric current and magnetic effect of electric current. Both we are going to discuss in this third chapter, effects of electric current. Now you know what is meant by heating effect of electric current. Now this heat effect is seen in the resistor W equal to VIT. This work done, we call it as the thermal energy, and it is stored in the resistors in the form of heat, that we call it as the heat energy. So the heat produced in the resistor, it will be equal to VIT, where E is the voltage given to the conductor and I is the current flowing in the conductor for a time t. By Ohm's law, we know that V equal to IR. Substitute this here. What happens to this equation V? H is equal to, if I substitute V equal to IR, it will become I square RT. Clear? Then I can also write this as I equal to V by R, isn't it? Here in the place of I square, if I substitute this I equal to V by R, if it is I, it is V by R. If it is I square, this V square by R square. What happens here? V square by R square into RT. 1 R gets cancelled. Here I will be getting H is equal to V square by R into T. So here H is equal to I square RT. H is equal to VIT. These three gives you the heat produced whenever a current flows in a conductor. Clear? These three we call it as the Joule's law of heating. These three we call it as Joule's law of heating. So if I summarize all this, look at this second and the third equation. I can summarize this and I can say the heat produced in a resistor when a current I flows in a conductor, I can say it is directly proportional to the square of the current. That means if the current is more, if the current flowing in a conductor is more, then the heat produces more. Isn't it, for a given resistance R? It is directly proportional to the resistance R for a given current. I can also define this like this. Then the heat produced, look at the third equation. Here the heat produced is inversely proportional to the resistance R for a given voltage. So these three we call it as the Joule's law of heating. Clear? This man Joule, he just discussed all this effects of electric current and he also verified this Joule's law. With a simple calorimeter experiment, he verified the Joule's law. So if they ask Joule's law of heating, you have to write all the three. H is equal to VIT, H is equal to I square RT, H is equal to V square by R into T. Now we are going to see the verification of this Joule's law. Verification of this Joule's law by a simple experiment using Joule's calorimeter. This is your calorimeter. Lead. side I have a thermometer. And here I have oil. Stirrer. So here we have just seen what is meant by Joule's law of heating. Joule's law of heating gives you the heat produced will be equal to H is equal to I square RT. This one we are going to verify using your Joule's calorimeter. Here this now here this is your calorimeter. Here this calorimeter consists of a resistance R. It is just kept inside a calorimeter. Here 2/3 of the calorimeter is filled with water. 2/3 of your calorimeter is filled with water. Here I have a resistance R and a stirrer. It is connected to this calorimeter. In the middle I have a thermometer to measure the temperature of the calorimeter and its content. The whole setup is kept in a wooden block to minimize the loss of heat to the surroundings. This is your experimental arrangement, and here the resistance R is connected to a voltmeter. In the external circuit, here the resistance R is connected to a battery, ammeter P, and to the resistance, there is a rheostat in series. Here we are using ammeter to measure the amount of current flowing in the circuit. This is your experimental arrangement of your Joule's calorimeter, and now we are going to verify this Joule's law of heating by the simple experiment. First one is your law of current. I am going to verify the law of current. Then law of resistance, then law of time. First one, law of current. Clear? Now to begin with, just press the key and you allow the current to pass through the calorimeter. First you measure what is the temperature of the calorimeter and its contents. Let theta 1 be the temperature of the calorimeter and its contents. Now I want to verify the current. So you keep the time of flow of current to be the same for the same resistance R. So these two I am going to keep it to be the same, and I am going to vary the current. So what is going to be changed here in verifying the law of current? Since I am going to verify the current, I will change that, and I will keep the time and the resistance to be the same. Now to begin with, first you measure the temperature of the calorimeter and its contents using this thermometer. Let the temperature be T1. Now for a time T, let it be 10 minutes or 20 minutes or 30 minutes. For 20 minutes I am going to allow some current to flow through the resistance R here. So let I1 be the current flowing through the resistance R for 20 minutes. After 20 minutes, you just check the key, then you take out and you measure the temperature of the calorimeter and its content when a current I1 is flowing through the resistance for 20 minutes. Now let the temperature be theta 2 and let W be the specific heat capacity of the calorimeter and its content. Now I can find out how much is the heat produced in this resistor R due to the flow of current I1. Since I am passing some current to flow through this resistance R, for a time t, it will produce some heat, isn't it? We are going to measure what is the amount of heat produced in this resistance R. That is measured by H is equal to, by the formula, H is equal to W, that is the specific heat capacity, into the difference in temperature. This is the initial temperature and this one is the final temperature. Theta 2 minus theta 1. So, by using this formula, I will find out how much is the heat produced by passing the current I1 for 20 minutes. Let that heat produced be I1. Now, again what I will do, I will pass I2 be the different current. It won't be the same as I1 initial current. Now, I am going to, I may increase the current or decrease the current. But the time of passage of current will be the same for the second part. Let I2 be the current flowing in the calorimeter for the same time t. Let I2. Again you find out what is the heat produced H2. Again you repeat the experiment for the current I3 and you find out what is the heat produced H3. In all these cases, if you see the ratio between this current produced and the current passed and the heat produced, this H1 by I1 square, the ratio between these two, it will be equal to H2 by I2 square and it will be equal to H3 by I3 square. The ratio will be the same in all the three cases. That shows the heat produced is directly proportional to the square of the current. This is your verification of your Joule's law. What is told in Joule's law? He told when a more amount of current is flowing means more heat is produced in the resistor. So, we have verified it experimentally. Then you go for law of resistance. Here in this law of resistance, since I am going to verify the resistance R, I will keep the time of passage of current to be the same. I and T to be the same and I will vary this resistance R. Clear? H is equal to, same thing here. You allow some current I to flow through the resistance R for the same time T. And you find out what is the heat produced in the first case. Let H1 be the heat produced for the passage of current I for the same time T and for the resistance R. Here, let R1 be the resistance. Now, you vary the resistance. Clear? And you find out what will be the heat produced in this resistance of value R2 for the same current and same time. Let that be H2. So, you repeat the experiment for different resistance and you find out what is the heat produced in all the three cases. If you see the ratio between these two, it will be the same. That is H by R. Here, H is proportional to R. So, I can write this H by R, H1 by R1, that is the ratio between the heat produced and the resistance will be equal to the H2 by R2, which is equal to H3 by R3. So, I can say this H is directly proportional to the resistance R. If resistance is more, the heat produced is more for a given current and time. If these two are same, I can say this H is directly proportional to R. Then you go for the third one, that is law of time. It is directly proportional to T. Here, I will keep the current to be the same and the coil also to be the same. I will vary the time of passage of current. So, what I am going to vary here? The time of passage of current I am going to vary here. Same procedure. You allow a current I to flow through the resistance R for a time T. Let it be 5 minutes. Clear? For the first time, T1. You find out what is the heat produced in the resistor when a current I flows for a time T. That is 5 minutes. For example, you find out what is the heat produced by the formula. It is equal to W T2 minus theta 1. Then you allow the current, same current to flow through the coil, same coil for different time. Let it be 10 minutes. You allow the current to flow for 10 minutes. It is T2 now. And you find out what is the heat produced. Let it be H2. You repeat the experiment for different times T3, 15 minutes and you find out what is the heat produced. In all these three, if you see the ratio between these two, that is the heat produced and the time of passage of current, it will be equal in all the three examples. H3 by T3. So, I can say this H is directly proportional to T, that is the time of passage of current. So, here we verified the Joule's law of heating. What is told in Joule's law? This H is equal to I square RT. We verified here And now we came to the conclusion what he told us correct. Clear? This is a 10 mark question, a simple verification for your Joule's law of heating. Now in this chapter we are just seeing about the heating effect of current. In our day-to-day life, can you say some examples where you can see this heating effect of current? In your everyday from morning to night you can see this here. Can you say some examples where you can see this heating effect of current? So many examples you can say at your home, your electric bulb, your electric heater, your electric iron. Whenever you just take your iron box, you switch on. What happens if you touch it with your finger, your hand, what happens? You can feel the heat. That only you are going to use to iron your dresses, isn't it? So what is that there? It is nothing but the heating effect of the current. Whenever current passes, there is a heating effect. Now we are going to see some of the practical applications or your applications of your heating effect of current. One good example is your electric heater, electric toaster, electric iron box, electric bulb, your fuse wire. So many examples I can say for the heating effect of the electric current. You will see here 3 very good examples. First one is your electric heating device. Electric heating device. Can you say some examples for electric heating device? The answer is in the question itself. Electric heating device. Electric iron, electric toaster, electric heater. All those are very good examples for electric heating device. If you see those heating elements in all those heating devices, you will use nichrome as a heating element. Why? Because nichrome is an alloy of nickel and chromium. It's an alloy. We already seen in the second lesson. What we have seen? Manganese and nichrome. It's a alloy. All the alloys, this alloy we are going to use for making standard resistance. Why? Because it is having large specific, what we have seen, temperature coefficient of resistance is low for this nichrome, isn't it? Here, in all these heating devices, we are using this nichrome as a heating element. Why? Because it has high specific resistance and a high melting point, and it is not easily oxidized. For these properties only we are using this nichrome, which is an alloy of nickel and chromium, is used as a heating filament in all the heating devices. So this is a very good heating element. It's an alloy of nickel and chromium. Why it is used as a heating element in all these heating devices? Because based on its properties, it has high specific resistance, it has high melting point, it is not easily oxidized. So based on these properties only, we are selecting this alloy as a heating device in so many electrical heating devices. Then if you go for this fuse wire, where you can see this fuse wire? Where you can see the fuse wire? What is the main use of the fuse wire? Can you say? What is the main use of the fuse wire? If a large amount of current flows in your electrical appliances, this fuse wire, it will help you to protect your electrical appliances from damage. This is the main use of using the fuse wire, isn't it? It's an alloy. Another thing that here this filament is a alloy of lead and tin, made up of lead and tin. So it's an alloy made up of, fuse wire is an alloy made up of lead and tin. Here, if you see the percentage of these two, lead and tin, lead is 37% and tin is 63%. So it's a fuse wire. Fuse wire is an alloy made up of lead and tin. Lead is 37% and tin is 63%. Again, if you go for the properties of this fuse wire, here it will be having high specific resistance, but you see the melting point will be having low melting point. Why? Because if large amount of current flows through the circuit, what happens? If large amount of current flows through the circuit, since it is having low melting point, it can't able to withstand that large current flowing through it. So what happens? It immediately melts because it has a very low melting point. It melts and the circuit breaks and it will become open circuit. If it is an open circuit, what happens? The current will not flow into the appliances at all. So this way I can safeguard my appliances from damage. This is the use of using fuse wire as an alloy in all your electrical appliances. It's the fuse wire made up of lead and tin. This one is very important. You will be getting in 1 mark. Yeah, it has high specific resistance and low melting point. And then go for the third one, that is your electric bulb. What is the main use of this electric bulb? Here also we are using the heating effect of current. So can you say what is the property of the tungsten wire? Here this is the filament we are using in the electric bulb. In all the electric bulbs we are using tungsten as the heating element. Why? Because it will be having very high melting point. Yeah, that is the main property of this tungsten, which is used as a filament in all the electric bulb. If you see the temperature of this, it is 3380 degrees Celsius. This will be the melting point of your tungsten, 3380 degrees Celsius. So what happens if current flows through this tungsten wire? It will be heated to a very high value. That is why it glows. Yeah, here also we are using the heating effect of the electric current. Temperature 3380 degrees Celsius. So all these are your applications of your heating effect of electric current. That is electric heating device, fuse wire and electric bulb. Then so far we have seen what is meant by heating effect of current and what is how to verify the Joule's law. What is meant by Joule's law? It is equal to I square RC, that and all we have seen verification, and what are the applications of the heating effect of current we are using in your day-to-day life. Now, using this electrical energy is converted into thermal energy that you are seeing in the heating effect. Using thermal energy, is it possible to produce an EMF? So, using current, that is electrical energy is converted into thermal energy, isn't it? That we have seen now. Electrical energy is converted into thermal energy. Thermal means heat. Using thermal energy, is it possible to produce an EMF? If I produce an EMF, again I will be getting a current, isn't it? What is the EMF? The difference of, or the potential difference between the two terminals of a battery in a open circuit. That we call it as a EMF. Yeah? So using thermal energy, if I produce an EMF, that we call it as the thermoelectric effect. Using heat I am getting the current. Thermo means heat. That we call it as thermoelectric effect. Yeah? That we are going to see. What is meant by thermoelectric effect? So what is meant by thermoelectric effect? Using heat energy, I am producing an EMF. If I produce an EMF, because of the EMF, there will be a current. That current we call it as the thermoelectric current. And this process we call it as the thermoelectric effect. Yeah. So far we have seen heating effect of electric current. Now we are going to see the thermoelectric effect. The current produced because of this thermo EMF is called thermoelectric current. Clear? So there are three effects where I can get this thermoelectric effect. First one is your Seebeck effect. So this man Seebeck, he studied the effect of electric current, that is the heating effect of electric current, and he discovered when two dissimilar metals, that is two different metals, when two different metals are formed like this, and these two junctions, if they are maintained at two different temperatures, what he did, he took two metals, should be different metals, and he formed two different junctions, and he maintained these two junctions at different temperatures. Now, if they are maintained at two different temperatures, let this junction be hot and let this junction be cold. So this one, let it be made up of iron and let this be made up of copper. Yeah. Now, when it is connected like this, here he produced an EMF. We can see some current is flowing in the circuit. This effect we call it as the thermoelectric effect, and this arrangement we call it as thermocouple. So what is meant by thermocouple? When I form two different junctions by two different metals, and if these two junctions are maintained at two different temperatures, what happens? An EMF is produced. That EMF we call it as the thermo EMF, and the current flowing because of this thermo EMF we call it as the thermoelectric current. And this effect we call it as the thermo EMF or thermoelectric effect. And this arrangement we call it as thermocouple. This arrangement we call it as thermocouple. Clear? Now current will be flowing at this hot junction from copper to iron. Clear? At the hot junction, how the current will be flowing? From copper to iron. Now I am going to exchange these two temperatures. That is, I will make this junction to be cold and I will make this junction to be hot. What happens if I reverse these two junctions? The current will be flowing in the reverse direction. So I can say this Seebeck effect is reversible. The Seebeck effect is reversible. So if I exchange those two junctions, if the junctions are maintained at two different temperatures, or if the junctions are reversed, the current will also be flowing in the reverse direction. So I can say Seebeck effect is reversible. This was discovered by the scientist Seebeck, and he studied for different pairs of metals how will be this thermo EMF. Clear? What he did? He just took different pairs of metals and he studied for different pairs of metals how will be the EMF produced in all the pairs, and he just listed all the metals in a series. That series he called it as thermoelectric series. What he called that series as? He called it as thermoelectric series. So he listed the metals like this: first one bismuth, nickel, lead, platinum, copper, manganese, mercury, lead, tin, antimony, silver, zinc, cadmium, iron and antimony. So like this he listed all the metals. See here, he just formed a series by studying the properties of different pairs of metals, and he listed all the metals like this. This series we call it as the thermoelectric series. The position of the metals in this series depends upon the temperature. Here the thermo EMF formed in the thermocouple depends upon the pair of metals and the temperatures of the junctions used. Here, if I select any two metals for forming a thermocouple, here bismuth and the last metal is antimony. So if I select these two metals for forming a thermocouple, the EMF produced will be large. So what it told, if I select any two metals which are farther away from each other, the EMF produced will be large. If the distance, if I select these two metals, they are not far away from each other in the series. If I select these two metals or these two metals for forming a thermocouple, here the EMF produced will be less. So if I select metals which are far away from each other from this series, in this series, then the thermo EMF will be more. Then the current flows from the metal which is occurring earlier to the metal which is occurring later. So here if I select bismuth and antimony for forming a thermocouple, the current flows from bismuth to antimony. So this is the way how he formed the series, and this series he called it as thermoelectric series. And what is meant by Seebeck effect? When two different metals are formed to form a thermocouple and the two different junctions are maintained at two different temperatures, an EMF is produced. That EMF we call it as thermo EMF, and this effect we call it as the Seebeck effect. Seebeck effect is reversible. And here we have seen what happens to the magnitude and the sign of the thermo EMF. Here the magnitude of the EMF produced and the sign of the thermo EMF, it will be depends upon the nature of the metals and the temperature of the junctions and the temperature of the two junctions. There is a hard and cold junctions. Then depending studying all the properties of this series, he just given a relation of this thermo EMF produced. So they are the thermo EMF of any thermocouple has the temperature dependence. It is given by the relation V equal to alpha theta plus half beta theta square. Alpha theta plus half beta theta square, where E is the thermo EMF produced. So here this thermo EMF produced in a thermocouple, it has a direct dependence on the temperature difference between the two junctions. But theta is the temperature difference between the two junctions, and alpha and beta are the constants. So what is here alpha and beta? They are constants. It depends upon the nature of the metal what you are going to choose for your thermocouple. So you have to know what is Seebeck effect, whether it is reversible or not. What happens when these two junctions are reversed? Current direction will be reversed. That is why it is reversible. Then what is meant by thermoelectric series? In this thermoelectric series, the metal which occurs earlier to the metal which occurs later, the current will be flowing from this direction. That is here for bismuth and antimony, bismuth to antimony current flow. And here the thermo EMF produced will depend upon the nature of the materials used and the temperature of the hot and cold junctions. Here this EMF produced will, that is the voltage. Here it will be directly dependent on the temperature. It is given by the relation V equal to alpha theta plus beta theta square. Now if the two junctions are maintained at two different temperatures, another man came and he told that heat is evolved at one junction and heat is absorbed at other junction. What we are going to see here in Peltier effect. That effect we call it as Peltier effect. The second one is your Peltier effect. Before going further, now I will take the temperature of the hot junction in the x-axis, temperature of hot junction in the x-axis, and here your thermo EMF produced in millivolts in the y-axis. And I am going to draw a graph between the temperature of the hot junction and the thermo EMF developed in a thermocouple, keeping the temperature of the cold junction to be constant. I am not going to change the temperature of the cold junction. I am going to increase only the temperature of the hot junction. So here I will start with the temperature of the cold junction. Let theta C be the temperature of the cold junction. If I increase the temperature of the hot junction, the thermo EMF slowly increases. Yeah? And it reaches a maximum value for a particular temperature of the hot junction. That I will take it as theta n. Yeah, this we call it as the neutral temperature. So at a particular temperature of the hot junction, this thermo EMF developed will become maximum. Clear? After that, even though I increase the temperature of the hot junction, this thermo EMF will not increase and it starts decreasing. So after this particular temperature, what happens to here? The thermo EMF it starts decreasing. At a particular temperature of the hot junction, this thermo EMF value becomes 0. That temperature we call it as temperature of inversion. Please remember this. So at a particular temperature of hot junction, thermo EMF value becomes 0. That temperature we call it as temperature of inversion. When the thermo EMF become maximum, that temperature we call it as neutral temperature. So you should know what is my neutral temperature and what is in the temperature of inversion. So when the thermo EMF becomes 0, that temperature we call it as temperature of inversion or inversion temperature. At a particular temperature, EMF becomes maximum. That particular temperature we call it as neutral temperature. So if you take any thermocouple, for example, I will take bismuth and antimony as two different metals for forming a thermocouple. Here for a given thermocouple, this neutral temperature will be the same, and this temperature of inversion it will depend upon the temperature of the cold junction. Yeah, that means if I change this temperature of the cold junction, this temperature of inversion also changes, but the theta n remains to be the same for a given thermocouple. So what you should know first in this graph, what we studied first, what is meant by the neutral temperature and what is meant by temperature of inversion. After this, if you increase the temperature of the hot junction, now the thermo EMF values become 0. What happens after this? If you increase the temperature of the hot junction, the EMF increases in the opposite direction. Clear? That's all. Again it becomes 0 at a particular temperature. That we call it as a temperature of inversion. Clear? Now you have to remember, for a given thermocouple, this neutral theta I, and that is the neutral temperature, will be the same, but this theta I, temperature of inversion, it will be changing. It changes, it depends upon the temperature of the cold junction. So these two values you should remember. This is very important. Now for large difference in temperature only, I will get this graph to be a parabolic graph. Clear? So for large difference in temperature between the hot and cold junctions, if the temperature difference is very large, the graph will be a parabola. What happens if the temperature difference between the two junctions is very small? I won't get a parabolic graph. I will get a straight line graph. When I will get a straight line graph, then the temperature difference between the two junctions is very less, very small. When the temperature difference is very large, what happens? To the shape of the graph, it will be a parabolic graph. So these are very, very important. And this relation between this temperature of inversion and neutral temperature and temperature of the cold junction, there is a relation between these three temperatures, that is theta I equal to theta C plus theta N, theta N, and then I will go for the last one, the relation connecting theta N equal to theta I plus theta C by 2. This is the relation connecting these three temperatures: neutral temperature, temperature of inversion, and temperature of the cold junction. So for a given thermocouple, you should remember this theta N will not depend upon the given thermocouple. It will be the constant. So here this theta I will be changing. It depends upon the temperature of the cold junction. This is very important one. Then the next effect we are going to see what is meant by Peltier effect. So the same thing, but he told, this man Peltier told, when two different metals are formed or made to form two different junctions, this is one junction and this is another junction. This is junction 1, this is junction 2. If two different metals are formed to form two different junctions, this is one metal, this is junction 1 and this is, here I have two different metals and I made two different junctions. He told, this man Peltier, heat is evolved at one junction and heat is absorbed at one junction. For example, this is iron and this is copper. At this junction 1, what happens? And at this junction 2, what happens? And this is heated. Here at this junction 1, that is here in this copper iron thermocouple, the current flows from copper to iron. So what happens to this junction 1? Here heat is absorbed. When heat is absorbed, it is becoming cool. So that is why the junction 1 is cool, and here at the junction 2, heat is liberated, heat is evolved, and this junction 2 will be heated. So here these two junctions are not maintained at two different temperatures. Here he told in Peltier effect, when two different metals are formed to make a thermocouple, heat is evolved at one junction and heat is absorbed at one junction. What he told? Heat is absorbed at one junction and heat is evolved at one junction. That effect we call it as the Peltier effect. Now, in this Peltier effect, what happens if I reverse the direction of the current? See here, the same thing, copper and iron. This is negative, this is positive, this is copper, this is iron. So these two are two different junctions. So what they told in Peltier effect? Here, when two different metals are formed to make two different junctions, heat is absorbed at one junction and heat is evolved at another junction. When heat is absorbed, the junction becomes cool. When heat is evolved or liberated, it will become heated. So one junction will be hot and one junction will be hot. Because of the difference in temperature, there is a potential difference. Because of that, an EMF is developed, a current will be flown. In this example, current is flowing from copper to iron in this direction. Now, I am going to reverse the direction of the current for the same pair of metals. What happens if I reverse the direction of the current? In the first example, this junction 1 is at low temperature, this is cool. Here this is hot. Now I reverse the direction of the current. What happens? This junction will be hot and this junction will be cool. Why? Because here the heat will be liberated and here heat will be absorbed. So this junction will become hot and this junction will become cool when I reverse the direction of the current. So current flows from copper to iron, that is in the opposite direction. So here when I reverse the direction of the current, what happens to this two junction? Here this also gets reversed. So I can say this Peltier effect is reversible. Like Seebeck effect, Peltier effect is also reversible. So how I can define this Peltier effect? When two different metals are formed to make two different junctions, heat is absorbed at one junction and heat is evolved at another junction. When I reverse the direction of the current, here the junction temperature also gets reversed. So I can say this Peltier effect is reversible effect. Now in this Peltier effect, when let H be the amount of heat energy produced or developed, here this heat energy developed when a current I flows through it for a time t. This way I can say the heat produced is directly proportional to the current flowing in the couple for a given time t. So if I remove this proportionality and I put equal to, I should introduce a constant. Let the constant be pi here, where pi is called your Peltier coefficient. So how I can define this Peltier coefficient? Pi, this is given as HIT, HIT. That is this amount of heat energy produced in a given thermocouple when a current I, when a current of 1 ampere flows in the circuit for a given time of 1 second. When a current of 1 ampere flows through the circuit for a time t, that is 1 second. So the unit for Peltier coefficient is volt. So this will be your unit for Peltier coefficient. So it's a constant value, it is equal to pi. When it becomes pi, it is equal to pi I t. Pi is called your Peltier coefficient. So you should know what is meant by Peltier effect. What happens if the direction of the current is reversed? The heat developed is also reversed. The temperature of the two junctions is also reversed. So that it is called reversible effect. So what is meant by Peltier coefficient? The definition of Peltier coefficient, its unit. These are very important in this effect. So far we have seen two different metals and two different junctions are maintained at two different temperatures and EMF is produced, isn't it? Because of that we are getting a current that we call as thermoelectric current. Now what happens when a metal is taken and it is heated? It is not heated evenly. It is heated so that the current is not produced or evolved. It is just heated in a uneven manner. If that is the case, what happens for different pairs of metals? Different metals we are going to see that we call it as a Thomson effect. We take a metal, I will take, for example, I will take copper here. This is your metal. In this direction, I am going to allow the current to flow through this metal. Here, at the center, this is the center of this metal. This one I am going to heat it using a Bunsen burner. I am going to heat this metal at the center point C. So I have taken the copper as the metal. Let I be the current flowing through this metal AB. Let C be its midpoint. Here I am going to heat the conductor. What happens when I heat this conductor? It is not heated evenly now. It is an unequally heated conductor. Now at the center only I am going to supply some heat to this conductor. Current is flowing in this direction from A to B. So when the current flows from A to B, we are going to see what happens to the heat produced or heat evolved. Where it is going to heat, where the heat is absorbed and where the heat is liberated. Now to take any 2 points, which are equidistant from the center C. Let these 2 points be M and N. So I will take 2 points M and N at equidistant from the center C. Now this copper rod is heated unequally. Clear? So the heat produced in this conductor is not equal. That is, the temperature of the conductor, that is the copper rod, will not be the same at all the points. That is the meaning for this. Clear? Now current is flowing from this in this conductor from A to B. When the current is flowing in this conductor from A to B, if you see the temperature at this point N and at this point M, you can notice that the point N will be at a higher temperature than the point M. So the point N will be at a higher temperature than the point M. So I can say B is at a higher temperature than the point A. That means here heat is absorbed. Here heat is liberated. So from A to C, heat is absorbed, isn't it? Because current is flowing in this direction. From C to B, heat is evolved or liberated. So this will become cool and this will become hot. So this effect we call it as positive Thomson effect. This effect we call it as positive Thomson effect. So what he noticed, when I take a copper rod and you heat it unequally, when the current flows from A to B, this point N will be at a higher temperature than the point B when compared to M. That is, B will be at a higher temperature than the point A. That means from A to C, heat is absorbed. C to B, heat is liberated. Clear? Now, what happens when the current flows from B to A? That is, I am going to reverse it. What happens when the current flows from B to A? Here, this point will be at a higher temperature than this point. M will be at a higher temperature than the point N. So, A will be at higher temperature than the point B. Here, heat will be absorbed, evolved. That is in the reverse direction. So, this was the effect here seen when current flows from A to B. That effect we call it as a positive Thomson effect. Now, in the second example, we take iron. He took iron and he found out what happens when this iron bar is heated unequally, the same manner how he did for copper. But same thing here, I will take the midpoint of C. Here I am going to heat the iron rod. Similarly, you take 2 points M and N, which are equidistant from the center point C, and let the current flows in this direction from A to B. So here also current is flowing from A to B. But here, what is the metal we are using? Iron. Here I use the metal as copper. Here in this iron, he noticed that when current flows from A to B in this direction, here the point M is at a higher temperature than the point N. What he noticed in this example, the point M is at a higher temperature than the point N. That means here heat is liberated and here heat is absorbed. Here, so I can say from A to C, heat is liberated or evolved, and from C to B, heat is absorbed. That is the reverse effect. Here for this metal, what he noticed in this copper, he can't able to see the same changes in this bar iron. Here from A to C, here it is absorbed, but here it is liberated. This effect, what he noticed in this iron bar, he called it as negative Thomson effect. Negative Thomson effect. Then you took one more rod and he took lead. First one copper, second one iron, third he did the same procedure for lead. Here also same thing here. I am going to heat this lead at the center and 2 points M and N, equidistant from C, AB is the starting and the final point. Current is flowing in this direction. See what he noticed in the lead, when current flows from A to B, here in these two examples, he found that N is at a higher temperature, here M is at a higher temperature. But whatever may be the flow of direction of the current, whether it is from A to B or from B to A, these 2 points M and N are at the same temperature. He can't able to found out any difference in temperature between these 2 points M and N. So here what happens to this Thomson coefficient? Here for lead the Thomson coefficient is nil. Here for these two, for copper it is positive Thomson effect. For lead, for iron it is negative Thomson effect. For lead, so here there is no difference in temperature, that is M and N are at the same temperature. Whether the current flows from A to B or from B to A, here we can found these 2 points to be at the same temperature. So here we call this effect as zero Thomson effect. So many examples I can say. He just studied all the properties and he grouped some metals which are having this property as positive Thomson effect and which are having this property as negative Thomson effect, and lead is the only metal which is having zero Thomson effect. Now there are so many examples I can say for positive Thomson effect and for negative Thomson effect. For positive Thomson effect, examples given are antimony, silver, zinc, cadmium, and for negative Thomson effect, platinum, bismuth, nickel, cobalt, all these are having negative Thomson effect. And lead is the only metal which is having zero Thomson effect, and for this reason only this lead is used as one of the metal in forming a thermocouple. Why lead is used as one of the metal in forming a thermocouple? Because it is having the zero Thomson effect. Yeah, so how I can define this Thomson effect? So initially we have defined what is meant by Seebeck effect, we have defined what is meant by Peltier effect, and now we are going to define what is meant by Thomson effect. What is meant by Thomson effect here? When a metal is heated unequally, heat is absorbed or evolved toward the material. In that way I can define this Thomson effect. So all the examples given in your reader for positive and negative Thomson effect, you be thorough, those are very, very important. So far what we have seen in this third chapter, first we have seen what is the consequence of current, electric current. Whenever a current passes through a conductor, because of the passage of current, there is a heat energy developed. That we call it as the heating effect of electric current. And whenever a steady current flows, there will be a magnetic field. Then I can get the magnetic effect of electric current. First, we have seen what is the heating effect of electric current and what is the Joule's law of heating. And we have verified this Joule's law of heating using a simple experiment called Joule's calorimeter experiment. And what are the applications of heating effect of current? What are the three we have seen? One is the electric heating device, that we are using nichrome as the heating element. Why? Because it is having high specific resistance, high melting point, and is not easily oxidized. And second one is the fuse wire, and third one is the electric bulb. In all this, what is the alloy you are using, and what are the properties? You should be thorough with all the three. Then we have seen what is my Seebeck effect, Peltier effect, and Thomson effect. In the Seebeck and Peltier effect are reversible. You see the remaining in the next class.